An electric current in any circuit creates a magnetic field which, whenever it changes, induces a current in the same circuit that opposes the change. This phenomenon is called self-induction. The effect of self-induction is larger in a coil of many turns, called a solenoid, precisely because it loops many times around the changing flux. That's why a solenoid is used as a symbol of self-inductance in an electric circuit, where an inductor may be an element like a resistor or capacitor.
Current increasing in an inductor causes an opposing electromotive force, according to Faraday's law. And since the flux is proportional to the current that creates it, that electromotive force is equal to minus a constant L times the rate of change of current. L is called the inductance of the circuit element. An inductor opposes and slows down the buildup of current in a circuit, while a resistor may cause the current to decay by dissipating energy.
Okay, so the inductor is going to oppose the change in current within the circuit. All right, they said it a little bit, the explanation is slightly off. Okay, so it's going to oppose the change in current within a circuit. So if you're trying to increase the current value, it's going to act in a direction that's going to oppose that increase. If you're trying to reduce the current value, once again, it's going to generate a current that's going to oppose that decrease in current. That's what it means. Okay, now that I said it, let me just visually tell you what I'm talking about. Okay, guys, I'm increasing the current value in this direction. As you're increasing the current value, what happens? The inductor is going to try to oppose that change in current value. So it's going to try to oppose that increase in the current value. So it's going to have an electromotive force. It's going to oppose the direction of the increase of the current. So what would happen if I were to try to decrease the current value? Current is still moving in this direction, but I'm reducing the value of the current. Once again, the inductor is going to oppose, it's going to act to oppose that change. So it's going to create an electromotive force in the same direction. So it's going to try to actually oppose that reduction of the current value. So if you try to increase the current value, it's going to come up with an electromotive force in the opposite direction of the current because it doesn't want the current value to increase. And the current is still moving in the clockwise direction, but now I'm reducing the value of the current. This time the electromotive force is going to act to oppose that change, which means that it's going to try to generate current in the same direction in order to prevent the decrease of the current. It's kind of, so it always acts in a direction that's going to oppose the change of the current value. All right. So this is known as the RL circuit. So the R is going to be your resistor and L is going to be your inductor circuit. So now you got the battery, the original battery. This is the original voltage source. That's what I meant to say. And this is the induced voltage. This is the voltage generated by the inductor. Okay. As the current is increasing in this direction, the induced electromotive force is going to point in the opposite direction to actually prevent that increase in changing current value. All right. I'm just taking a look at this one. All right. You got your switch. You throw the switch on. As soon as you throw the switch on, what's going to happen is the voltage and the current is going to gradually build up. It's like charging a capacitor. It's the same idea. The reason why the voltage or the current is going to gradually build up is because the inductor is going to try to oppose that change in current. All right, so it's going to gradually build up to its maximum value. And then you take the switch and throw it off. So in this case, the battery is no longer part of the circuit, and there's a resistor within that circuit. So what happens to the current value? So current is going to decay in this case, which means that the current value is going to start to diminish. And this time, once again, the inductor is going to act to oppose that changing current value, diminishing current value. All right, so it's just going to slow it down. So the current is going to decay exponentially. All right, so mathematically, how do we do that? All right, so what does an inductor do in a circuit? Inductor is just going to oppose any build-up or reduction of current. If the current value is building up, it's going to oppose it, which means that the current is going to build up gradually. That's what it means. So if you have an inductor inside a circuit, so what happens to your current value? Your current value is going to gradually build up to its maximum value. All right, so this represents the maximum value of that. So in this case, the current is building up gradually. This is an RL circuit, so you got the resistor over here, you got the inductor over here. So you got the battery, so the current is going to start to build up, and then inductor is going to oppose that increase in current. This turns into a first-order differential equation, so it's differential equations is not required at this level, so I'm going to just take you to the final result. Okay, so this is the final result. This represents the maximum current value. It's going to build up to a maximum current value that you're looking at. All right, so this is voltage. The voltage is what drives current. So this will be the maximum current value that it's going to build up to. Just like the capacitor charging equation. This one is a current build-up equation that we're looking at. So this is the maximum value of the current that it's going to build up to. There's an exponential term that we're looking at. The exponent has to be unitless. T has the units of time, so which means that R divided by L has to have the units of time as well. All right, L divided by R is known as the inductive time constant, T sub L. All right, so this is known as the inductive time constant. Just like the capacitive time constant, the inductive time constant is going to tell you how fast the current value is going to build up. Technically speaking, it's how fast the current value is going to build up to 63% of its maximum value. All right, so it's related to how fast the current value is going to build up. The larger the inductance is, the longer it's going to take. All right, so the larger the inductance is, the more the inductor is going to resist the increase of the current value. The larger the resistance is, the smaller it's going to take, evidently, because the current is going to decay fairly fast. That's what it means. So that's your inductive time constant. All right, so when you remove the battery from the circuit, this time the current is going to decay, and inductor is going to actually add to reduce the decay of current. Okay, it's going to add to stop the reduction of the current. So which means that the current is going to decay slowly. It's going to from its maximum value. Once again, it turns into a first order differential equation. So I'm just going to skip that. This is the current axis. This is your time axis. So the inductor is going to slowly decay the current. So there's an exponential decay, and that exponential decay is represented by that equation. So this is the maximum value of the current, and the maximum value of the current is going to decay exponentially. And you got the inductive time constant. So inductive time constant is going to tell you how fast the decay is going to take place. All right, let's do a simple problem regarding this one. Okay, so problem number 3. Let's do this one. On problem number 4, let me check to see which one is a little bit more interesting. Okay, problem number 4 is related to the energy stored in the magnetic field. Okay, so I'm gonna skip that one or way down that one. Let's focus on problem number 3. All right, so before we do problem number 3, okay, so number 1, okay, let's get back to problem number 3. So what are we dealing with? So we're dealing with a solenoid. It's got an inductance value. Okay, let me just list everything first. Problem number 3. All right, so the inductance is given to us in terms of millihenry. Okay, so we also have the resistance value in terms of ohms. So it's connected to your battery. So the current is going to build up. And we want to know the amount of time it's going to take for it to build up to the half of its final value. All right, so figure out the amount of time it's going to take for it to build up to half of its value. All right, so figure out the time in terms of seconds for it to reach the half of its value, maximum value. So this ratio is going to be 1/2. Okay, so millihenry. Okay, so this needs to be expressed in terms of Henry. So it's going to be 53 times 10 to the minus 3 Henry. Okay, so that's the only conversion that we needed. All right, so what are we dealing with? We're dealing with the current value is actually building up. So the current is going to be gradually building up in this one. All right, so the scenario that we're looking at involves an RL circuit that's going to have a battery in it. So you will have a resistor, and then you will have an inductor. This is the inductor symbol. And the current is going to be building up in this direction. All right, so the current is going to be building up to its maximum value. So the question is, how long will that take? All right, so here's the maximum value of the current. So it's going to be T sub L. All right, so and we know that the inductive time constant is going to be the ratio of the inductance to the resistance. All right, so the only thing we have to do is just isolate it for T. The reason I keep doing these kind of problems, this is more of a manipulation of equations. Well, one of the reason you're not supposed to be struggling with this sort of algebra, but people do for some reason. All right, I'm not going to use any numbers. Once again, I didn't get a chance to look at your test yet, but I think it's going to take you a while before you guys know how to show work properly. Don't use numbers until you get to the final equation. All right, just get used to doing it that way, because most of you guys will start taking 300-400 level courses. No one wants to see numbers in reality. The only thing we want to know is, hey, given these are your initial parameters, can you come up with a finalized equation into which you actually plug these numbers in? All right, there. And then can you explain why you're solving a problem in the way that you're solving? Okay, so I provided you an explanation. I said, hey, the current is going to build up because there's an inductor here. And this is how it's going to build up to its maximum value. And this is the equation that represents it. In a variation of the current is going to cause an electromotive force. And the electromotive force is going to point in a direction which is going to oppose any change of the original electromotive force. All right, so that means that because it's going to act in a direction that's going to oppose any change, you're going to be able to store energy inside the inductor. Okay, so I'm going to skip the details of these, and I'm going to move on to the very last final equation. All right, so this represents the amount of energy which is going to get stored inside the inductor that we're looking at. I want you to notice that the bigger the inductance is, the more energy is going to be stored in it. The larger the amount of current is, the more energy is stored in it, but most importantly, the larger the inductance is, the more energy is going to be stored in it. Okay, so I want you to just remember the formula. The derivation is not that important at this point, but remember the formula, the importance of the formula. All right, so larger the inductance value is, which is related to geometry, the more energy it's going to be able to store. And the energy, once again, is going to be stored within the magnetic field inside the inductor. The energy is going to be stored within the magnetic field inside the inductor.